Hi, I'm Granny, and we're going down the rabbit hole of the magnetic poles and the auroras. Yes, we learned last time that the Earth is one huge magnet, and scientists are still trying to figure that out. There are theories, but there's no absolutes. So, from what science knows now, we're going to learn about what the magnetosphere is. The Earth's magnetic field, also known as the geomagnetic field, is generated in our Earth's interior and extends out into space, creating a region known as the magnetosphere. Magnets, sphere, and there is a connection between the magnetic poles and what is referred to as the auroras. Last time we mentioned that Bernard Bruns, a French geophysicist who was born in 1867 and died really young in 1910, and learned by studying ancient lava flows in 1905 that the magnetic poles switch. And I use the idea of this magnet. There's a positive and a negative. Understanding that and applying it to our entire Earth and the magnetosphere, that the Earth switches or reverses its polarity, the positive to the negative, negative to the positive poles. But also in 1831, we learned that there is a difference between the magnetic North Pole and the geographic North Pole. And it was Sir James Clark Ross who discovered that in northern Canada. So the term aurora borealis is from Galileo, and he's another rabbit hole that we need to go down. He named the lights from the Greek word north wind, borealis. And so the northern lights are called the aurora borealis. The southern lights are called the aurora australis, Australia. The auroras are created when solar wind from the sun flows towards the earth, chemically reacting to the Earth's atmosphere. Let's step back just a little bit. When you breathe, what do you breathe in? Most air is composed of about 21% oxygen, 78% nitrogen, and a mix of argon and carbon dioxide in a variety, depending upon how many particles are in the air. So when the sun has a chemical reaction, because the sun is just a huge ball of chemicals reacting to each other. It isn't like a fire that you throw logs on and it lasts a couple hours. The chemical reactions going on in and on the sun's surface and inside are called coronal mass ejections. So you can go and see pictures, NASA produces lots of them, of a CME, coronal mass ejection, that shoots out from the sun, goes towards the earth, and then when it hits our magnetosphere, those chemicals react with our magnetosphere, our chemicals from the Earth's magnet, and creates what is called the auroras. The more visible the auroras, the larger the CMEs are on the sun. There are many times when the CMEs make it possible for the northern lights to be seen in the lower, like the lower 48s. For instance, Canada often can see it, but you normally have to be in the higher mountains like in Utah or Nevada or Colorado to be able to see it here. According to spaceweather.com, there are on average 10 solar flares in a year. According to NASA, the frequency of the solar flares varies with the 11-year solar cycle. Now, last episode we discussed how when the polarity of the Earth reverses its polarity, It's ranging from every 200,000 years to 800,000 years. Well, the magnetic activity on the sun is in a more dependable or regular pattern of 11 years, as long as we've been studying it. So, and you'll remember that it was studying ancient lava flows that we learned that the magnetic poles switch polarity in a very unpredictable time manner. So again, back to solar flares. When there is what is referred to as a solar maximum, you can have several flares, CMEs, a day. And then when it's the solar minimum, meaning not so much activity, they're less powerful. All right, so the auroras result when charged particles streaming from the sun, CMEs, collide with the molecules on the Earth or in the Earth's atmosphere, chemically reacting with each other, causing colors. So the different colors, according to scientists, that the sun particles penetrate the Earth's magnetosphere and collide with the nitrogen and oxygen atoms in our atmosphere. It's all a chemical reaction. Actually, a lot of things in our world are chemical reactions. Did you ever think that cooking is a chemical reaction? But it is. Because if you were to take a cake from scratch, throw everything together, mix it, it won't come out as a cake. There's a process. Well, it's the same thing with the auroras. Several factors are involved, and the colors are created at what point in our magnetosphere that the particles from the sun collide with our magnetosphere. So to get green, the sun's particles hitting the oxygen in our magnetosphere up to 150 miles in altitude. The red is created at 150 miles and above. Nitrogen, blue, in the auroras is up to 60 miles, reacting to our nitrogen. Purple, it has to be above 60 miles above the Earth's surface. So the magnetic forces and the electrical forces are moving and reacting to each other, resulting in the auroras, and they're constantly moving in the sky. So you'll see colors, but you're almost seeing wind because it's like flowing water. Wind is like flowing water. And the only time you really see it is if there's clouds. You can watch clouds. But in this case, it's chemical reactions that look like wind. Thus, that's why the Galileo called it the north wind. So in the next episode, we're going to learn if a solar flare can cause telegraph lines to melt or roosters to crow in the middle of the night. But that's another rabbit hole. So if you would like to join me, I put out videos every Thursday, and I hope you join me for my next episode of When Granny Goes Down the Rabbit Hole.